Good afternoon. Welcome to the week 6 video, on air pressure and winds. And I want to start off by saying that this video that you're watching for week 6, please refer to chapter 9. That's chapter 9 in your textbook, the 7th edition, Aaron's Invitation to the Atmosphere. Please refer to chapter 9 for week 6. All right, so today we're going to talk again about air pressure and winds. All right, so the first thing I want to mention is air pressure. What is air pressure exactly? It is the mass of air above a given level. And as we climb in altitude above Earth's surface, there are fewer and fewer air molecules above us. So the number of air molecules spreads out immensely as you get higher up in the atmosphere. This atmospheric, basically the further spreading apart of these air molecules results in atmospheric pressure decreasing with increasing height. So if you were to go in a hot air balloon or in an airplane, you would notice a definite change in barometric pressure, air pressure in general, with height. It would be much lower the higher you went up. If you were to take an instrument called a barometer up with you, go up, if you were a hiker or you went up a huge hillside or mountain, you would notice a drastic drop in the air pressure as you continue to climb up that mountain. Now, our atmosphere is a highly compressible, and it's a mixture of gases, which we've already learned is highly compressible gases. Most of it is squeezed closer to the Earth's surface. Most of the density and air pressure is confined to a shallow layer of the atmosphere. This causes air pressure to decrease with height. When you have most of the air molecules packed more tightly near the Earth's surface, the air pressure again decreases with height, rapidly at first and then more slowly at higher altitudes. Now, just as there are vertical pressure changes with height, there are also horizontal pressure variations. This requires a shorter column of dense, cold air to exert the same pressure as a taller column of less dense, warm air. So you do have horizontal pressure variations. In addition, warm air aloft is normally associated with high atmospheric pressure and cold air aloft with low atmospheric pressure. So if you were to go above a surface high pressure system, if you continue to go up with height, you would notice that there's warmer air aloft. If there was an area of lower pressure on the surface and you went up with altitude or height, you would also notice in that case it would be colder air aloft. Now, heating and cooling of air columns can establish horizontal variations in the air pressure both aloft and at the surface. Atmospheric pressure. This diagram showing you what a typical air column would look like. Each one of these little dots in the air column there, the tallest portion of the diagram, generally indicate air molecules. So just in general, air molecules, air columns, there are differing levels of air columns based on the temperature of those air columns, and the packing of those molecules is also going to vary based on the temperatures. Here are differences in air columns based on temperature alone. If I were to look at, for example, the middle diagram there, and I have a warmer column of air on the right, indicated in that pinkish color. On the left, there is a shorter cold air column there, middle part of the diagram. So City 1 has a colder air column over it. City 2's got a warmer air column over it. Do you notice that the warmer air column is going to be much taller in the vertical because warm air wants to expand? It is less dense. And those air molecules, those little dots in that warmer air column, are further apart from each other. They're spread out greater distances as compared to the air column, that shorter air column on the left at City 1. Now, if you have differences in air pressure, and this is kind of tying in with what we just went over, if you have surface high pressure, generally your air column is going to be warmer air aloft, and so your air molecules are going to be much further spread apart again, and the packing of those air molecules is going to be much further apart. As compared to on the right hand side there, City 1, with surface pressure rises, you notice it's a colder air column because you're having more packing of the air molecules closer to the Earth's surface. When you pack it in and shorten the column of air, you tend to cause surface pressure to want to rise. Whereas if you have a warmer air column and it expands, there's going to be less force per unit area or a surface pressure fall with a warm air column. All right, now looking at measuring air pressure, all right, how do we measure the force exerted by the air molecules over a given area? Well, we measure air pressure with an instrument known as a barometer. This measures bars. Now, bars are units of pressure that describe a force over a given area. So barometric pressure, or the standard atmospheric pressure, is 1013.25 millibars. Aneroid barometers are a special type of barometer, which basically means no fluid or no liquid. So aneroid barometers are typically what you'd see at home. A lot of people can buy these from the hardware store. You'll see a lot of people with them in their homes as decorative pieces. They have the dial and the hand on it and all that. I'll show you what this looks like here in a minute, hopefully. I think I have some pictures to show you what the different barometers look like and how they work. But again, aneroid barometers, most common home barometer, what you see typically at a lot of homes, and they contain no fluid. All right, moving on now to atmospheric pressure, showing you some of the changes in pressure. Now, this particular diagram shows a mercury barometer. A mercury barometer has a liquid mercury in the tube. Okay. On the right-hand side, I'm showing you just some standard pressure levels that have been recorded and observed, some pressure levels around the world. All right, so 1013.25 millibars, or 29.92 inches of mercury, is a standard sea level pressure. And we learned that in an earlier unit. Now, the pressure has got as high as 1085 millibars, or 32.03 inches of mercury. That is the highest recorded sea level pressure, and that occurred in, looks like Mongolia in December of 2001. If I go on the other extreme here, let's see, we'll go down to the bottom, 870 millibars, or 25.70 inches. That is the lowest ever recorded sea level pressure, and that was in association with a major hurricane in the Western Pacific. In the Western Pacific, they are called typhoons, but it's the same principle. Typhoon Tip in October 1979 had the lowest recorded atmospheric pressure out of everything. Looking at deep low pressure systems, kind of in the middle there, a 980 millibar low, or a 28.94 inches of mercury low. That's a deep low pressure system. A strong high pressure system, which we would typically see in the wintertime when the air is coldest and most dense, that was about 1040 millibars, or 30.71 inches of mercury. So just showing you some comparisons to atmospheric pressure. Okay, now we're going to take a look at the mercury barometer a little bit more in depth. So you notice that there is a glass tube that contains this liquid mercury in the center of it. Okay, and there's little increments, increments you can read on this tube that tell you what the atmospheric pressure is. Generally what happens is when the air pressure is greater, or there's more force per unit area pressing down, as those blue arrows indicate at the base of the drawing here, shows arrows pointing down into the mercury in the dish there at the base. The air pressure, if it's pushing down, is going to exert greater force, and that is going to cause the mercury in the glass tube to rise. So the higher the mercury rises in the glass tube, the higher the barometric pressure. And then if, let's say, the air pressure wasn't pushing down on the base there of this mercury barometer, then the air pressure would tend to want to fall or sink in the tube. Right, so this is the premise and the operation and the functionality of a mercury barometer. You may have seen some of these before in previous science classes. For example, when you were in high school, maybe your physics teacher or your chemistry teacher may have had one of these in their room. Okay, this, on the other hand, is an example of an aneroid barometer. Aneroid again means without liquid, without fluid. This has a dial. It's usually a dial, a dark dial. You'll see how the dial changes in accordance with these amplifying levers in the aneroid cell, which is contained within the aneroid barometer. You really can't see it. It's usually covered up. But there is an aneroid cell in there that responds to changes in the barometric pressure. All right. And whenever the pressure is higher, you'll notice the dial, that black dial there, there's descriptive terms on the face of the aneroid barometer, such as stormy, rain, change, fair, and dry. So the higher the pressure goes, usually the dial will point to the descriptive words. If it's a higher barometric pressure situation, higher than 1020 millibars, usually you'll see the dial pointed towards fair. If it's less than 1010 millibars, usually see change or stormy. So these are quite common again in homes. You can get all kinds of different styles of aneroid barometers to hang on your wall. You can find them typically at a hardware store. You can also find them, I've seen them before even in like Walmart or some of the retail outlets like that. This is another instrument that we use to measure atmospheric pressure, and this is called a barograph. Now the cool thing is with this particular device, it has an amplifying lever. It changes according to the fluctuations in the aneroid cell. Okay, so when the pressure is higher, the response of the lever will be more weight will be pushed down the lever, and that will cause you see the little blue line, that rotating drum, the ink trace on the left. The paper rotates on a cylinder, it kind of just moves around, and that blue line indicates a written or recorded history of the barometric pressure on that sheet of paper, and that is known as a barograph. It's just basically a special type of barometer that keeps a continuous history of the barometric pressure. Okay. Now let's move into pressure readings. So for pressure readings, there are instrument errors. So each mercury barometer, for example, has its own built-in error, caused in part by the surface tension of the mercury against a glass tube. So bottom line is there's errors in the instrument. There's slight errors built in. And so basically we have a couple special cases of how we correct for those errors. One is station pressure, and station pressure is simply barometer reading at a particular location and elevation after being corrected. So station pressure, there's going to be a different station pressure, for example, in Denver, Colorado, because it's basically 5,280 feet above sea level, or 1 mile high. That's why they call Denver the Mile High City, because it's at an elevation of 1 mile above sea level. So your station pressure in Denver is going to be different as compared to, say, the station pressure at a location like New Orleans, where it's at sea level. A city at sea level like New Orleans is going to have a different station pressure than Denver. So that corrects, it's a barometer reading at a particular location and is correcting for that elevation difference. Altitude corrections, these are made so a barometer reading taken at one elevation can be compared with a reading taken at another. And then even in airplanes, when you fly an airplane, pilots have a special type of barometer known as an altimeter. An altimeter is basically telling the pilot how high or how low they are flying above mean sea level. Okay, so here we're taking a look at the differences again in station pressure. It's going to be much different. For example, we have a couple points here on the diagram, point A, point B, and point C. So A is at the top of the smaller hill on the left, and you'll notice how below the actual diagram there of the hills, you'll notice that there's different sea level pressure charts at the very bottom there. That just shows you the differences in the sea level pressure based on height. Generally, the station pressure is going to be different. It's going to be lower at higher altitude locations as compared to a location close to sea level. So we do have these special conversions and calculators and calculation tables that we can use to convert, let's say, the pressure at Denver as compared to New Orleans. We can take into account that elevation difference to come up with a more distinct reading. All right, now on surface and upper air charts, that's our next topic we talk about. Upper air, they're also known as isobaric maps. And an upper air chart is basically one that has constant pressure on it. It's constructed to show height variations along a constant pressure surface. Now, there are features in the upper levels of the atmosphere that we must pay attention to for weather. There's areas of upper low pressure, upper low height centers, and there's upper high height centers. So we have these contour lines, which basically are lines to connect points of equal height on these upper air charts. So contour lines of low height represent a region of lower pressure, and then contour lines of higher height on the upper level charts represent a region of higher pressure. Okay? So here's how things tie in. On the left, I'm showing you an image of a surface weather map. You'll see the blue H represents a surface high pressure system, while the red L will represent a surface low pressure system. Now I want you to notice the upper air map, and that's at 500 millibars on the right. Now 500 millibars is generally equated to about 18,000 feet above mean sea level. All right, so notice in the eastern United States there over southern Illinois, the blue H, that represents a surface high pressure system. Look at the chart on the right and notice that it is associated with what's known as upper level ridge. So ridges in the upper levels generally support your surface high pressure systems, the blue H on the left. And then the surface low pressure system there over parts of Idaho and Montana, notice on the right hand chart there, the upper air chart on the right, how there's an area of, there's an L stamp there, and there's a dipping down of your height contours. That is known as an upper level trough. So surface low pressure systems are supported by upper level troughs, while surface high pressure systems are supported by upper level or upper air ridges. Okay? And one thing I wanted to mention on the right here, you see these 55, these lines, these darker lines, these darker solid lines, those are the lines, those are the contour lines I was just mentioning in the previous slide. So, you know, these are lines of equal height. Each line represents a certain level of height in the atmosphere. So 5460, that's in meters. That's an example of a height. You'll see that line kind of go bend down and then up over the top of that ridge. 5520, 5580, 5640, and 5700 meters. Those are all examples of height contours. Okay. Whereas on the left, the darker lines represent isobars. So we measure surface pressure in isobars, and we measure upper level heights with height contours. All right, now let's talk about why the wind blows. You may have wondered, hey, it's breezy out here today, it's really windy, while on other days it's not so windy at all. And that has to do with some of the causes that have to do with pressure gradient forces, which we'll get into. But let's first start talking about Newton's laws of motion. So Newton's laws of motion, an object at rest will remain at rest, and an object in motion will remain in motion as long as no force is exerted on the object. Okay, so this is the law of inertia. For example, think about yourself in the morning when you're, in a nice deep sleep. The alarm clock goes off, and you're kind of thinking to yourself, "Man, I do not want to move. I am tired. Oh, how I wish it wasn't Monday." Okay. That's an example of Newton's first law of motion, the law of inertia. You want to remain at rest. It takes more energy and more work to get you out of bed, to get going, to start the day usually, as compared to when you're already out and about and walking throughout your day, doing your daily activities at work or whatever activities you have. All right, so just remember this, an object at rest will remain at rest, and an object in motion will remain in motion as long as there's no external force which impacts that motion of the object. Another law of motion we need to talk about is the force exerted on an object equals its mass times the acceleration produced. So that's force equals mass times acceleration. And acceleration refers to the speeding up, slowing down, change of direction of an object. Right, so what forces influence the wind that we feel every day when we go about our business? The first one I like to talk about is pressure gradient force. And the pressure gradient force is either termed steep or gentle. You'll hear the term steep pressure gradient or a gentle pressure gradient. The pressure gradient force is that net force acting on the air when differences in horizontal air pressure exist. Keep in mind that we have areas of low pressure and high pressure. And due to those differences in air pressure, the wind blows. And the wind is always going to blow from higher to toward lower pressure, and typically it's going to blow at right angles across the isobars. The reason this happens, it blows at right angles to the isobars, is because of the force of friction. As wind blows across the surface, there are trees, there are buildings. The ground itself is going to slow that wind speed down to a certain extent, and that's due to the force of friction, right? So that's going to cause your pressure gradient force to basically be deflected across the isobars at an angle, generally from higher toward lower pressure. All right, so here's an example of two tanks I'm showing you just to illustrate this, the net force, the pressure gradient force that sets up from high to lower pressure. If you notice on the tank on the left, I have a lot more water in it, and water is a very dense substance. So the higher the column of water, the greater the density exerted downward on the bottom of this tank. All right, and then you notice on the right-hand side here, I have less water in the tank, so therefore it's going to be less dense and it's going to be lower pressure. So if I were to connect these two tanks side by side, one that has more water in it, higher pressure, and connected to a tank that has, tank B here, that has lower pressure and less water in it, you will notice that the flow will go from tank A to tank B, from the higher pressure tank to the lower pressure tank. And go ahead and try this at home sometime. If you have two objects, and go ahead and fill one up in a closed cylinder, higher up, and with more density, more water, fill it up with the water, and on the other one, keep less water in it, and just see what happens once you connect these two together. Now, in the atmosphere and on the surface pressure weather maps, the surface charts we call them, or surface weather maps, you'll notice that you have a pressure gradient force that is going to blow from high toward lower pressure. Always the case. Now look at the 1020 millibar, that's an isobar, and then you have 1016 millibars, that dark line, that's another isobar or line of equal pressure. An isobar is simply a line of equal barometric pressure. So the net force from the high to the low across a distance of about 100 kilometers, point 1 to point 2, is generally from high to low pressure. All right, so with high pressure systems, we generally have winds blowing outward, away from the center, and you'll see the pressure gradient force that is basically moving outward from higher towards lower pressure. You notice the pressure at the center of the high here, or the isobar surrounding the high, is at 1024 millibars. And then the further out you go, you'll notice that the isobars are less and less, or the pressure is less and less. The isobar value drops, starting at 1024, dropping down to a value of 1016 millibars. So all the pressure is exerted outward, away from the center of higher barometric pressure at the center of the high, outward away from that. Okay, you notice it's 90 degrees across the isobars in this case. Here's an example of an actual surface weather chart. Okay, these lines surrounding this red L, or low pressure system, generally are known as wind barbs, which show you the wind direction. Okay, there's a chart here on the right that shows you what the different wind barbs mean. The different little lines on the wind barbs indicates how many miles per hour or how many knots of wind speed you have. All right, so in this particular diagram, we have an area of low pressure situated off the coast of New Jersey. Its central pressure is 943 millibars, and then you go outward away from that low and the pressure gets higher and higher. So air pressure generally blows inward toward the center of low pressure, surface low pressure. You can see how these wind barbs are pointed generally towards the low pressure system. No matter which way you go, it's a counterclockwise circulation around the low pressure systems in the northern hemisphere. But all the wind is blowing from higher towards the center. All the wind barbs are generally pointing across the isobars at an angle because of friction, but generally blowing inward toward low pressure. Another force we have to talk about when we talk about wind is Coriolis Force. Coriolis Force is an apparent force due to rotation of the Earth. Generally, Coriolis Force operates right of intended path of motion of an object in the northern hemisphere and to the left of the intended path of motion in the southern hemisphere. Keep in mind that the Coriolis Force is an apparent force. It's not a real force, it's an apparent force that's caused by the fact that the Earth is rotating beneath the wind. The wind is not permanently fixed to the surface of the Earth, and the globe and the Earth itself is rotating counterclockwise from west to east. So this generally results in a turning of an object to the right of its intended path in the northern hemisphere and to the left of its intended path in the southern hemisphere. A couple things to keep in mind. The stronger the wind, the greater the deflection. Zero value of Coriolis force at the equator, and it reaches its maximum value of Coriolis force at the poles. The amount of deflection depends on Earth rotation, the latitude, and the object's speed. And Coriolis force is going to act at right angles to the wind. Okay? I have a better diagram here showing Coriolis force a little bit better. So the top two circles here on the diagram, we're generally looking over the top of somebody situated on a merry-go-round or a spinning circular object. All right. On the bottom, we're showing you I'm showing you a non-rotating platform on the left and the view from above on the upper left. So the bottom left and the upper left diagrams kind of match up for a non-rotating situation. And on the right, I have a rotating situation. So if you notice on the left-hand column, the left-hand side of the diagram, how if you have two people sitting on the outer edge of this merry-go-round, if they were to throw a ball towards each other, generally that ball is going to appear to move in a straight line because it's not rotating. So imagine you're just sitting on a platform, a merry-go-round for example, that actually could spin around, two people sitting on the edges, throwing the ball back and forth to each other. Okay, it's not rotating, so everything appears to be moving in a straight line. Now, on the right-hand side, if we start rotating that object in a counterclockwise manner, and you have the two people still sitting on the edges of this merry-go-round, and they throw the ball towards each other, it's going to appear to deflect to the right of its intended path of motion if it was spinning around. All right. So hopefully that better helps explain the Coriolis force. If you have a rotating Earth, a similar thing happens. Everything tends to get deflected to the right of intended path in the northern hemisphere and to the left of intended path in the southern hemisphere. Okay. And then Coriolis force also comes into play. There's generally zero Coriolis force at the equator. So you notice the airplane on the left, the aircraft's intended path generally parallels the equator or the lines of latitude. Okay, but if you have an actual situation where the Earth is spinning, it appears that the plane is gone right of its intended path, basically its direction in the northern hemisphere because of that rotation. All right. In the upper levels of the atmosphere, in those upper air charts, we also have to talk about why the wind blows in a straight line flow. So we have something known as geostrophic winds on the upper air charts, which can be estimated directly by observing the orientation of the isobars on upper level chart. When the flow of air is purely geostrophic, the isobars, or when we talk about geostrophic flow, I'm more inclined to talk about upper level charts or upper air charts. The contour lines. When the flow of air is purely geostrophic, those contour lines are going to be straight and are evenly spaced, and the wind speed is constant. Geostrophic wind blows parallel to height contours. I'm going to change this wording because this is going to throw you off. I'm going to say geostrophic winds. I want you to think about height contours and upper air charts only. Okay? Geostrophic winds blow parallel to height contours. Because guess what? On upper air charts, you have no force of friction. So there's no turning of the winds across height contours like there is on the surface. On the surface, you have the wind blowing across the ground. As it blows across the ground, it's slowed down by the force of friction, and the pressure gradient force will be directed from higher toward lower pressure at an angle across the isobars because of friction. But on the upper air charts, your geostrophic wind blows parallel to the height contours because there's no force of friction to turn or change that wind. So here's an example, just showing you, I'm looking at, actually it looks to me like I'm looking at a surface chart here. Everything blows from higher towards lower pressure. The pressure gradient force will basically be, you see the red arrows there, that's the pressure gradient force. If I show a parcels trajectory represented by the purple line over the ground, you'll notice that everything is directed from higher on the bottom towards lower on the top. You see the red L? Generally higher towards lower pressure. The red arrows indicate the direction of the pressure gradient force as a result. But as you have that motion, you also have to factor in the Coriolis force, which if you look at the top part of the diagram there, as the air parcel turns at the different points 1, 2, 3, 4, and 5, notice that the Coriolis force acts opposite to the pressure gradient force. Basically, it blows at directly to the right. It turns to the right of the parcel's intended path of motion. So Coriolis force actually opposes the pressure gradient force when we talk about an air parcel on the surface and its movement. And then generally we talk about, I'm just showing you a stream example here on the left. It's similar with a stream. When the stream is wider, you generally have weaker flow. Okay? When that stream on the left narrows though and gets more constricted in its ability to move, you're going to have stronger and faster flow. I'm showing you the corresponding upper level chart on the right to that stream. You notice that the height contours, these black solid lines, are further apart. That indicates similar to the stream on the left where you have weak and slow flow. Once you constrict or bring closer together those height contours on the right, your wind is going to accelerate or pick up. All right. And again, notice from higher toward lower pressure, pressure gradient force, that red arrow on the right-hand diagram, from higher toward lower pressure, and the Coriolis force acts equal and opposite to that pressure gradient force when you have geostrophic flow. All right, now we're going to talk about curved winds around lows and highs aloft. Generally, with cyclonic flow, you get a counterclockwise circulation of air around a low, and then with anticyclonic flow, you get a clockwise flow of air around a high. And then we have something known as a gradient wind. It's wind that blows at constant speed parallel to curved isobars above the level of frictional influence. So when we talk about gradient wind, we're talking about on the upper air charts once again. All right. With gradient wind, we have curved flow. So it's like if you were driving in a car around a curve on a road. Imagine you and your car are that air parcel. So as you go around different curves, you're going to feel different forces involved, usually centripetal force and then centrifugal force. But we won't really get into that in this discussion. But just imagine if you're driving in a car and you have to go around a curvy road. When you go around those curves, it's similar to air parcels going around curved isobars or height contours. And that is called a gradient wind. Okay. So whenever you have curved flow, you add a new element here, and that's called a gradient wind. We're looking at upper air charts, by the way. We're looking aloft, above this ground on this particular diagram. Notice that the pressure gradient force again acts inward toward lower pressure. Pressure gradient force is directed inward towards the low. Centrifugal force, Coriolis force is always going to act to the right of an intended path of the parcel. So you see CF there, the blue arrow. So Coriolis force acts equal and opposite to the pressure gradient force. And then over time, when you have curve flow, you also you see these blue arrows on that in letter C, that diagram letter C. You see that the purple arrows and how they flow parallel to the curved isobars or height contours. Okay, so that's a gradient wind example. Winds in upper level charts, winds tend to blow parallel to contour lines because we don't have any friction. They generally flow west to east. Winds on upper level charts flow from west to east in the mid latitudes, and your general upper level heights are going to decrease or get lower as you go from north to south. Okay. Surface winds, winds cross the isobars. When we're talking about winds blowing on the ground now, I'm going to go back one real quick here. I don't want to confuse anybody, but actually the heights decrease from south to north. That's a typo. I'm glad I caught that. The heights actually decrease from south to north. They get lower as you go poleward or towards the northern latitudes. So don't be fooled by that. I apologize for that typo in there. Now moving on to surface winds again. Generally, the winds are going to blow across the isobars at about a 30-degree angle. The pressure gradient force is going to direct those winds across the isobars from higher toward lower surface pressure. Friction reduces the wind speed as that wind blows across the surface. Again, imagine trees, building, houses. All these objects tend to reduce the effect of wind speed on the surface because of friction, and in turn will result in a decrease in the Coriolis effect. So the lower the wind speed, the lower the Coriolis effect. The higher the wind speed, the greater the Coriolis effect. Just like with latitude as well. The higher the latitude you get, the farther north you get, the greater the Coriolis effect. The closer to the equator you get, the less the Coriolis effect. Okay, just want to put that out. All right, so now here we're taking a look at a chart. This is an upper level chart, or upper air chart. Okay, this is a 500 millibar chart at about 18,000 feet above mean sea level, above the ground. Generally shows you these darker lines on here are your height contours. So you can see on the right hand side there of the diagram, they're labeled 5820, 5760, 5700, 5640, and 5580. So you notice your heights will decrease as you go further north. They decrease from south to north, the heights. Okay, and that's what I corrected on that previous slide. Also notice that these red lines, these red dashed lines, are lines of equal temperature. So those are isotherms, okay, lines of equal temperature. So an upper air chart such as the 500 millibar chart at 18,000 feet is going to show you the basic height contour pattern with its ridges and its troughs, as well as your temperature patterns. Usually with troughs you have colder air aloft, and with ridges you have warmer air aloft. All right, now winds and vertical air motions. Air generally again moves inward toward the center of a low pressure area, and then converging air cannot go into the ground. So when the air meets and converges towards the center of a low pressure system, kind of meets up like this head on, it can't go down below into the ground, so it must rise in the atmosphere. So above the surface low pressure system, we generally have air that wants to rise. The air begins to spread apart or diverge higher up above the surface low. Okay. There's something known as hydrostatic equilibrium that I just wanted to mention briefly. This is when you have an upward directed pressure gradient force. So think about it in the atmosphere in the vertical. Generally closer to the surface, we have the air molecules packed much closer together. So naturally, we have higher surface pressure at the ground. But aloft, remember I talked about at the beginning of this lesson, aloft, those air molecules become more widely spaced and there's less pressure. We mentioned how the pressure decreases rather rapidly initially, will continue to decrease with height, the pressure. All right, so we have something known as a hydrostatic equilibrium in which your vertical pressure gradient now, higher pressure at the surface, lower pressure aloft, the direction of your pressure gradient in the vertical is going to be from the surface up. So you're going to have upward directed pressure gradient force from higher toward lower pressure aloft. And that's an exact balance with the downward force of gravity. So gravity is always acting down, and then the upward directed pressure gradient force is acting up. So when these two are kind of equal and opposite to each other, we term that phrase hydrostatic equilibrium. All right. Here's a quick diagram of the surface features and then what's happening aloft over the top of them at higher altitudes above the ground. So the lower diagrams here, and we have diagram A and B, just showing you generally what's going on. So again, at the ground there in diagram A, you have high pressure on the bottom, the blue H, the red L, the low pressure, kind of like in the upper part of the diagram. Remember that the pressure gradient force is always directed from higher to lower pressure. So you see the red PGF standing for pressure gradient force, directed from higher toward lower pressure. You see the arrow pointing towards the low pressure. And then you have the Coriolis force, which is acting to the right of the intended path of that motion. And then you have a frictional effect. As winds blow from high to low pressure, that frictional effect results in the winds blowing about 30 degrees across the isobars, or lines of equal barometric pressure. Aloft above that, you'll see that you have generally a geostrophic wind. And so geostrophic wind there in diagram A shows you that the winds are blowing parallel between higher and lower heights. blowing parallel to the height contours. And then you have, when you have a geostrophic wind, everything is in balance aloft in the upper air charts, where you have pressure gradient force directed from higher to lower heights, and it's directly balanced equal and opposite by the Coriolis Force, CF. In diagram B here, I'm showing you an area of surface low pressure. Notice how the winds spiral inward, counterclockwise, inward towards the center of low pressure. And above that low pressure system, you'll see an upper air trough, and that's represented by that dip, that little dip, that almost like a U-shaped pattern. And there's an upper level low, upper level trough that supports that surface low pressure system. On the right hand side, the far right, I'm showing you an area of surface high pressure, and you'll notice how the winds blow outward and away from the center of the surface high pressure. So diverging air, and you generally have an upper level high above the surface high, and an upper air ridge supports that surface high pressure system. And then I'm showing you some other just general differences here between northern and southern hemisphere. This is a southern hemisphere picture off of South America. So the wind flow is just opposite. For anticyclones or high pressure systems in the southern hemisphere, they tend to blow counterclockwise circulation around the high and outward away from the high, whereas the cyclones in the southern hemisphere have clockwise circulation around them. It's the opposite to the northern hemisphere, and they generally blow inward towards the low pressure system. And then I'm going to show you a quick picture here of winds and vertical air motions. So surface low pressure systems on the left generally have converging air at the surface. The air must rise. Rising air then cools, condenses, forms clouds, and usually precipitation. You'll have divergence, or the spreading out or removal of mass over the top of low pressure systems, and that's designed to counteract the converging of air at the ground. With high pressure systems at the surface, you usually have air that diverges or spreads apart, and you have upper level air that's converging. It's the exact opposite with high pressure systems. Upper level air converging over the high, and as the air meets, it must go downward. As it goes downward, you have sinking air, usually clear skies with high pressure systems and nice weather. Right, something else we must mention now: how do we determine wind direction and speed? Since we've been talking about the forces that create winds, the pressure gradient force, we must also talk about how wind direction and speed. How do we determine it? So wind is characterized by direction, speed, and even gustiness. The wind direction describes the direction from which the wind is blowing. So please keep this in mind. If I say the wind is a northerly wind, that means the wind is blowing from the north. If I say the wind is a southerly wind, that means the wind is blowing from the south. So please keep that straight in your mind. I know it can be confusing at times. Generally, wind direction describes the direction from which it is blowing from, and it could be onshore if you live near a body of water. That's where the wind's coming in during the day with a sea breeze off the water. Or it could be offshore, where the wind's blowing off from land to water. Offshore is land toward water. Upslope could be in a situation where you live in the mountains, upslope and downslope. If it's upslope, the wind is generally blowing up the mountain. If it's downslope, it's moving down the mountain. An example of a downslope wind that we're very familiar with in the United States is the Chinook wind of Colorado. All right, so here again, just showing you some diagrams of difference between onshore and offshore. An onshore wind is generally blowing from the water toward the land, and an offshore wind on the right is blowing from land toward water. Determining wind direction, we usually use these the common compass rose. You'll notice that we divide the compass rose into four main directions: the north, east, south, and west. And then we divide that further up into northeast, southeast, southwest, and northwest. And then we can even further divide that up into directions such as west, northwest, north, northwest, north, northeast, east, northeast, and so on. Now, I want you to make sure you remember the degrees associated with each wind direction, mainly the north, northeast, east, southeast, south, southwest, west, and northwest. So, for example, if I have a wind from the northwest, the wind's generally blowing from a direction of 315 degrees on the compass rose. If I have a wind blowing from the north, my wind is generally blowing from 360 degrees. If I have a wind blowing from the southeast, my wind is blowing from 135 degrees. Southwest, 225 degrees. West, 270 degrees, and so on. So this is how we determine wind direction using a compass rose. Now the influence of prevailing winds. Prevailing winds, what are those? That's the wind direction that's most often observed during a given time period. And believe it or not, prevailing wind has quite a few applications that we may not think about. For example, runways at airports are orientated a certain way based on the prevailing winds for that area. For example, I'm in Virginia, and I live in Southeast Virginia, and many of the runways at the airports, local airports, generally run 320 to 140 degrees, and that is mainly because we generally either have a northwest or southeast wind the majority of the year. So again, prevailing winds come in handy when planning is involved in construction of buildings. For example, where you plant trees in relation to your house, runway applications like I mentioned, how airports are laid out. And prevailing winds can greatly affect the climate of a region, there's no doubt about it. Upslope winds, if you're in a mountainous area, if you live on the windward side of a mountain, you're generally going to have a much wetter climate, cooler and wetter climate on the windward side of a mountain as compared to the leeward side of a mountain where there's downslope wind. So think about things, upslope, rising, cooling air, it makes clouds, fog, and precipitation, and it's more likely than where the winds are when they go downslope on the leeward side of the mountain. It'll be much drier and warmer. Here's an example of trees in prevailing wind directions, okay? You can see the way these trees are, the overall branches are pointed towards in this diagram, generally from left to right. So if I were looking at this picture, I should be able to determine the prevailing wind direction, and it would be basically from left to right across this image because how you see the branches pointed. All right, now what are some common wind instruments we have out there? All right, wind instruments are really cool instruments. We have a wind vane, which is going to give you like the wind direction. And if you're in rural areas or if you've ever been near a farm area, country, there are a wide variety of decorative wind vanes out there. You see them a lot in the farm areas on top of barns. It generally it's free to pivot, this wind vane, and the arrow generally points into the direction from which the wind is blowing from. But there's a lot of cool little decorative things out there, like some wind vanes are roosters. I've seen some that were horses on farms. I've seen some that are really, really cool. I mean, you can almost like get a specialized wind vane. Again, the whole premise is that wind vane is going to spin freely and it's going to point into the direction from which the wind is blowing from. The anemometer, it measures wind speed. Generally, you have rotating cups, and they generally spin in a circle. The faster those cups spin, the greater the wind speed. Aerovanes, another cool little instrument. Raw wind sounds, wind soundings. Now, the raw wind sound and the wind soundings and the wind profilers, those are to measure the changes of wind direction and height in the vertical. So if I were to launch weather balloons, I used to launch weather balloons as part of the Navy job, which is really cool. You fill up the balloons with helium. They have these little transmitter boxes. You attach it to the neck of the balloon once you get it all zip tied shut, and then you release the balloon, and that transmitter, that little box, instrumentation box, measures your temperature, the humidity, the wind direction, and speeds with height, and then it transmits that signal via GPS back down to a raw wind sound. The raw wind sound, there's an N missing after the I on that, by the way. It's not spelled correctly. But raw wind sound is a box that actually shows the readout as your weather balloon goes up aloft and is measuring your elements, temperature, humidity, wind direction, and speed with height. Okay, the pressure, what the pressure is up at higher altitudes as well. So that raw wind sound is your basic box that sits right in front of you, and it'll be spitting out all this data to you when you're sitting there watching, after you launch a weather balloon. So that's really cool. And SQT diagrams generally are generated. The vertical profiles of temperature, winds, all that with height is generated through a weather balloon and a transmitter attached to that neck of that balloon and transmits it down to the raw wind sound instrument. Radars, we're very familiar with radars. You know, we turn on the TV news, we see the TV weatherman up there showing the latest Doppler radar, where the precipitation's at, how heavy is the precipitation, where is the precipitation moving. These are all common uses of a radar, a weather radar, Doppler radar. And then satellite imagery, it's huge. You know, just being able to see hurricanes on the distance, out over the ocean and where they're moving, kind of look at their changing characteristics, their shapes. You know, is there an eye? Satellite images tell us a lot of our weather over the lower 48, the United States as well, for impending storm systems. So basically, to kind of wrap up this week 6 lesson, I'm going to show you a few different wind instruments. This is a combined, see the rotating cups there on the upper left, this is a combined wind vane slant anemometer. So the instrument on the right hand side that has that little pointer, that is your wind direction. It's going to freely rotate or pivot, and it's going to point towards the direction from which the wind is blowing. The upper left-hand diagram shows an anemometer, rotating cup anemometer. Those cups will spin freely. The faster the wind blows, the faster those cups will rotate. Okay, and that's going to register a readout on an instrument, tell you what the wind speed is. Here's an example of an Aerovane. It kind of has a propeller, almost like a little airplane, right? This propeller will rotate and spin quicker when the wind blows faster. If there's hardly any wind, it'll just kind of sit the way it looks. If the wind was calm, it would look like that. And it generally is free to rotate and pivot in any direction, but it'll point into the wind. All right, that's an Aerovane. Gives us both wind speed and direction. And then you have this instrumentation here. Just generally has like little poles and stuff on it. Generally, it can sense the motion of air as it goes across these little pins and needles and poles. And determining wind speed and direction is so critical, especially when we talk about major storm systems such as hurricanes over the ocean. You know, we have different special instrumentation on our weather satellite on our weather satellites. Believe it or not, we have sounders, microwave imagery. We have all kinds of neat tools that can tell us the wind directions and speeds around major low pressure systems such as hurricanes, like this one here. This one is actually a southern hemisphere hurricane because the wind direction is generally clockwise around it, which is really cool. It's not really a northern hemisphere situation here. All right, so in summary, today we talked about air pressure. We talked about instrumentation, the barometer, and how it measures air pressure. We talked about two types of barometers, the aneroid barometer without liquid. We talked about the mercury barometer, which is the tube with the liquid, mercury liquid inside. We talked about, in addition to air pressure, what causes wind. The wind is caused by the pressure gradient force, or the differences between higher and lower surface pressures. And remember that wind always blows from higher toward lower pressure. So pressure gradient force is always directed from higher toward lower pressure. We talked about Coriolis force and the fact that it's an apparent force that deflects objects to the right of their intended path in the northern hemisphere. Coriolis force generally tends to act equal and opposite in a lot of cases to the pressure gradient force. And then we talked about instrumentation with winds, wind instrumentation. All right, we talked about upper air charts as indicated here in the summary slide. Aloft, where horizontal variations in temperature exist, there's a corresponding horizontal change in pressure. Once air is set in motion, the Coriolis force bends the moving air, again to the right of intended path in the northern hemisphere, to the left of intended path in the southern hemisphere. We talked about the interaction of the forces causes the wind to blow in different directions. And then various methods and instruments are used to measure wind speed and direction. We talked about an anemometer with those rotating cups on top. We talked about the general standard wind vane, raw wind sounds, and upper air soundings. We talked about an Aerovane. All right, so I really hope you enjoyed this lesson on pressure, force, winds, and the instrumentation used to measure them. And I'm really hoping you're I'm really hopeful that you're enjoying the course as a whole, and I look forward to continuing on and continuing to move forward in this exciting world of weather. All right, that wraps things up from me for week 6. Week 6, remember to use Chapter 9 in your textbook for Week 6. All right, everybody, take care. Until next time, have a good one.